In the previous video on trigonometric substitution, we were seeing a definite integral, an integral that had specific numbers and limits of integration, and we saw that when we did our trigonometric substitution, we had to be a little bit careful with changing those limits. In this video, I'm going to show you another example of a trigonometric substitution, but this time it's going to be an indefinite integral, and it's going to turn out that the final step, the step that involves transforming the variables back into the original variables, has a little bit of a nuance to it. So the example that I want to look at is going to be the integral of 1 over the square root of x squared minus 1 dx. So the first thing we want to figure out is what is going to be an appropriate substitution here. I want to have my x variable equal to some trigonometric term. Well, one of the things that I can go through my list of canonical Pythagorean identities is that if I have tan squared plus 1 is secant squared, then manipulating it around, I'm going to have that secant squared of theta minus 1 is going to be equal to tan squared of theta. And the reason I'm writing this down is I have something which looks like x squared minus 1. So if I set x equal to secant of theta, then hopefully this is going to work out. I'll be able to take the bottom thing and say this is the square root of tan squared, and everything's going to work out nicely. So that's why I use this particular substitution. I'll also note that we know what the derivative of secant is. It's going to be secant theta tangent of theta d theta. When we do our substitution, it's very important to change the dx as well. Okay, so now we want to look at the restriction on the domain. And the essential thing that matters here is that we have a square root. So we don't want to have square roots of a negative number. In other words, my x squared minus 1 always needs to be positive. We need to have the x squared minus 1 greater than or equal to 0. And this gives us two possibilities on x. It tells us that either my x is a value that's bigger than 1, or my value of x is less than minus 1. One of those two possibilities. Okay, so that's what is demanded for us from the x variable. So what restriction does that mean that we put on for the theta variables? Well, I can do a little bit of a graph of secant of theta, just sort of a back of the envelope sketch of secant is going to look a little bit something like this. We know that secant's 1 over cos. Cos goes from 1 to 0 as it goes to pi over 2. So if I put in a point here like pi over 2, if cos goes from 1 to 0, then my secant goes from 1 to infinity. So it goes up like this. Oops, there we go. We have some spike like that. Next, cosine as it goes and heads over towards pi. And I'll put maybe 3 pi over here as well. If we go between pi over 2 and pi, well, cos is going between 0 and minus 1. So 1 over cos is going minus infinity and minus 1. So it looks like this. And the rest of the graph I'll just sort of fill in like that. So this was the graph of secant of theta, in particular x equal to secant of theta. So for x being greater than 1, that looks like, for instance, that branch right there. And I can write this down by saying these are the thetas between 0 and pi over 2. So I want my theta being between 0 and pi over 2. So that's the one case. The other case is when x is less than minus 1. Well, I could choose, for instance, this region here. That's a section where it's well defined. There's only one value where it's going to be less than minus 1. Or I could choose this region down here. It doesn't really matter. I'm going to choose this latter region that I've selected, and I'll show you why it matters in just a moment. I'm going to make the other region being this one between pi and 3 pi divided by 2. All right, so I had a choice. I just had to choose one region that take all the different values. It could have been pi over 2 to pi, could be pi to 3 pi over 2. I'm going to choose this one, and we're going to see why in a moment. Okay, so let's flesh out the computation. We've decided to use x as secant of theta, so this is going to be the integral, well, dx, we decided, is secant theta tan theta d theta, that's the derivative of secant. And then in the denominator, it is the square root of secant squared of theta minus 1. And what do we get? Secant theta, tan theta on the top. And now we have secant squared minus 1. That is the same thing as tangent squared of theta. And now the choice of our restriction is going to become relevant. You'll notice that we have 0 to pi over 2 is one of our regions, and by the way, tangent, which is sine over cos, both sine and cos are positive in that region, that's going to be a positive. Likewise, between the pi and 3 pi over 2, both sine and cosine are negative, and therefore tangent is again positive. So what I get to note is that the square root of tan squared, which is the same thing, if I just take this denominator, that's the same thing as the absolute value of tangent of theta. This is the same thing as just tangent theta on those domains that I chose. 0 up to pi over 2, or pi up to theta up to 3 pi over 2. So if I had chosen differently, that is, I set pi over 2 to pi to be one of my regions, then I would have had to break this up into two different cases. In one case, the absolute value of tan theta would be tan theta, and in the other would be minus tan theta. So this choice of restriction just makes everything work out a little bit nicer. All right, so carrying on with my computation, my tangents are going to cancel. This is just going to be the square root, or the integral rather, of secant theta d theta. Now, this particular integral is not an easy one. If you want, you can look up in the book. There's a weird trick that applies to this particular integral you can do, but it's not one that I'm going to expect us to know. So I'm just going to quote for us the answer here. The answer turns out to be ln of secant theta plus tangent of theta plus c. So, copying and pasting, I'll note that I'm not quite done here, because the problem is my answers are still written in terms of theta and not in terms of x. And this is the real thing that I wanted to demonstrate, is how to deal with this. Now, if I go all the way back to the beginning, we had that x was described to be secant of theta. Or in other words, this is 1 divided by cosine of theta, or another way to write it is cosine of theta is going to be equal to 1 divided by x. Now I write this because I want to know how secant and how tangent relate back to x. And I have a relation, a trigonometric relationship. I know what cosine of theta is, so I should be able to figure out what secant of theta is and what tangent of theta is. So now what I'm going to do is use this to make a triangle. I'm going to put in my theta in some triangle, and then I have that the adjacent over the hypotenuse is 1 divided by x. So I'm going to put a 1 here, I'm going to put an x here, and I'm going to put a square root of x squared minus 1 on the side that I hadn't figured out. That is me applying Pythagoras. And if I try to figure out, say, tangent of theta here, I already know secant of theta is x, so I don't have to convert that one. But for tangent of theta, I can say that tangent of theta is opposite over adjacent, so square root of x squared minus 1 all divided out by 1. And now I can come back up here and I've got all of my conversions. This is ln of the absolute value. Secant of theta is just equal to x, so this is just going to be an x. And then tangent of theta is described down here, so the square root of x squared minus 1 all plus c, and that gives me my final answer. So at all points in this course, if I have an indefinite integral where I don't specify the limits, the agreement that we're going to have is that we're going to write the final answer in terms of the original variable. In this case, my original integral was given in terms of x, so my final answer should be in terms of x, and not any intermediate substitution variables like theta or u or anything else. So that's what I've done in this step. This conversion between thetas and x's is to write it in terms of the original variable, and I'm allowed to use a sort of trigonometry to make that happen.